And Zainab is my PhD student, graduated, has gone back to Libya. So I'm going to present what we did a few years back. Okay, before we go on into the techniques, the transformation techniques, so I'm going to go through what is option all about. Okay, option is a contract that gives its holder the right, but not the obligation, to exercise the option with the writer. So we are talking, all of you now are the shareholders. You are not the shareholders, you have something. Okay? So in real financial markets, we are talking about finance. Three most popular ones, popular options are European options, American options, and Asian options. What I'm going to do today is, I'm going to talk about, about the arithmetic Asian option. So basically, Asian option we have two. One is geometric and the other one is arithmetic. But what I'm going to focus on today is the arithmetic. Thank you very much. Lots of words, but now I have to drink. I'm still here. I'm not lost in space. Okay. All right. So just a quick definition of what European option is. An option which can only be exercised at the maturity date. So what is exercised? Exercise means you want to buy or you want to sell the specific amount, and you will stock, commodity, currency, or debt at a specific price. Okay? Asian option. An option whose payoff function depends on the average of the stock price over the life of option. Basically, maturity date, life of the option, or expiration date are all the same. Okay, what are the payoff? Is the value of option at its expiration date. Okay, you will see all the worms after a few more slides. Do you know what the worms are? It's going to be the Blackscholes PDE, and you have all those del over del S squared and everything. Okay? No, the worms is not yet here. So everybody was thinking, what are the worms? Okay. Alright, so the American option is an option which can be exercised at any time up to the maturity date or life of the option or expansion. Okay. I'm getting older, so I have to, use my glasses, and then when it's going to be far away, I have to take it out. Okay? Okay. Option, we have two, call option and put option. So call option is the option that gives you as a shareholder the right to buy the underlying asset, and also for the put option, it will give you the right to sell. Okay, so you have two. It's going to be quite a lot of types. So we have call option, put option, and then we have arithmetic call and put option, and then we have geometric call and put options. Okay, strike price. I hope everybody at the back can see. It's a little bit lower. The strike price, which is the fixed price at which the holder of the option can purchase if it is call option, and it can sell if it is a put option. So this is the period of time that I mentioned earlier. Life of option is the same as the expiration date or maturity date. Okay. Who is the person who's giving us all this problem? The PDE, okay? That we have to find the solution to this problem. So there are this Fisher Black, an economist, definitely when we talk about finance, and Myron shows a mathematician. So this is a combination work between these two fellas, investigated a new method for pricing European option, where this formulation or this model are named after these two guys, this economist and mathematician, named Blackscholes formula for option pricing. Okay, slowly we are getting into it. Okay, it is a mathematical model actually that is investigated to describe values of European call and put options, or Maybe I can say values of European options, which would include the call and the put. Okay, bear in mind, please, I will ask 2 questions at the end of the class. So I'll see class, and I have two prizes to be given away. I think everybody will start jotting down. I know. Okay. All right. Blackscholes model is basically a second-order partial differential equation. Something ringing? The PDE, right? With 2 variables. Okay? Solution of this model provides the value of European options at every single time. And this model, the Blackscholes model, was later improved to deal with some limitation of the real market and extended to another types of option, and that type of option is the one that we choose, the Asian option. Okay? Maybe you are living in Malaysia, so we have to start thinking of Asian. We are not staying in Europe, right? Okay. Maybe some of you do a few years back, right? Okay. So the model suggested by Blackscholes is to describe the behavior of prices in a continuous time model. Okay. We have 2. That is the risk-free asset, also called a bond. I think everybody has heard of bond. Okay. We represent with BT, and the one risky asset called as stock, ST. Alright, so I think everybody has seen this ODE. Everybody knows how to solve it, right? In order to get this BT equals to B naught exponent of RT, right? You are going to use what method? Separation of variables. Good. My class is very good. Okay, which means an investment of B naught in a bond gives an amount of B naught exponent RT, and since we said it is risk-free asset, therefore, it's always, what is this scanning still here? How do I close it? Okay. Alright, always have a positive return. So people might ask me, what happens if it is a negative return? Okay, negative return will only happen if our economy is very, very, very bad. Yeah. Negative returns mean you're going to lose something, right? So means if the risk-free means you will always get a positive return. We are not going to be bankrupt, right? Alright. Okay, now we look at the stock price, ST, of the underlying asset. Okay, this is the stochastic differential equation that will lead us to the Blackscholes. And I'm not going to talk about the when the sigma is 0, because again you will get the ODE, which is very simple to solve. So what we're going to see about is whenever the sigma is greater than 0, the stock can have a positive or negative return. Alright. Here we go. This is the European call options. Rosanara, I have another half an hour, right? Okay, alright. Okay, by using Ito's lemma, okay, I think if anyone is interested in Ito's lemma, you can see me later. I have that also, but I'm not going to go through the Ito's lemma because the technique of that transformation will take some time because of all the worms, right? Okay. Now we go to just now we were talking about the option, and then I introduced about the European option. It is a model of Blackscholes with 2 variables. Remember? Now, Asian options, we have 1 extra variable. So Asian option is going to be a formulation of a PDE with 3 variables. Okay? So what are the third one? I'm again lost in words. Okay. It's a kind of path-dependent option whose payoff depends on the historical average of the underlying asset. So the average, or which I will use A, is the other variables that will be included into the PDE. Okay, I'm not going to read this one. You have the notes. Okay, bear in mind that some of the notes there's a typo at there, and I've already like corrected some of it. Okay. Okay. Now this is the one that I'm telling you about. The types of the Asian option. We have the arithmetic and we have the geometric, and each and every one also have the call and the put option. Okay. This is to purchase. This is to sell. Right. And so that's for the geometric. Okay, if the average is considered now, you're talking about what is the small definition of what is the geometric Asian option is. It has a log normal probability density, and in this case there is a closed form solution. Means you can find the solution. Not that hard. So anybody interested, you can check with Baruchi et al. 2001. But if the average is considered to be a running sum or the arithmetic average of the underlying asset price, then we get the arithmetic Asian option. So this is the one that we are dealing with, because it is a challenge in order to get the closed form for the analytical solution. So it is a little bit out of place, because what I'm going to do now is the analytical solution. But don't worry, one of my PhD students here, Powesi, he is going to do the numerical part of it. So the analytical has been done by Zainab, my previous PhD student, and Powesi is going to continue with the numerical solution. Okay? Okay. Now, that's what I was telling you just now. We have 3 independent variables, which is time for T. I colored it blue to blue, red to red, and green to green. Okay? Just like my daughter, I have to do that in order for them to see the relation. Okay? So you are all just like my daughter maybe. Okay? Not my grandchild, definitely. My grandchild is only about 2 years old, so you are not 2 years old, definitely. Alright, Asian option can be classified as a discrete or continuous time, but in this work, we will only consider the model with the continuous time Asian option, because we're going to use the Blackscholes model. Right? Okay. Here it comes. This is the Blackscholes PDE of the Asian option. Okay, now, I haven't said anything about, for this particular PDE, I haven't said anything about average or, the arithmetic or geometric. Okay? So now, the phi is the payoff function at the maturity date or the expiration date, where A of t is defined as the integration of f of su du. As you can see, the fs here is not yet being represented by any function yet, because this fs is going to determine the 2 different kinds of Asian option, whether it is geometric or arithmetic. Right? So if A is considered to be a geometric average of the asset price, whereby the fs is ln of s, therefore we get what is called as geometric Asian option. Okay, this is the representative PDE of the geometric Asian option. Okay, it looks so messy, right? Later, when we do the transformation, we will slowly get a better represent or model. Okay. Now, this is the running sum. Let's say A is considered to be a running sum of the asset price. Remember, you are now all the shareholder. Okay. So bear in mind, you are doing something with stock price or whatever. Okay. So AT is represented by SU, and this is, you see, the FS here now is the S, and this particular PDE is going to be used later on in our transformation technique to get the analytical solution. Okay, again, if A is assumed to be the arithmetic average of the asset price, we will have 1 over t integration of SU du, and the PDE is going to be as equation B here. Okay, basically this particular PDE is being created by Roger and She. Okay, and actually this particular PDE also has been solved by our group a few years back. Okay. Okay, A and B, the A and the B are the Blackscholes PDE for the Arithmetic Patient option. Okay, now we reach to the stage where you will see a lot of worms, del B, del A, and then it will be changed because we are going to do quite a number of change of variables, and then we will use the transformation. Okay? Okay. We will use a lot of this equation 1. Okay? S is the stock price at time t, R is the interest rate, sigma is the volatility, and T is the maturity date or expiration date. So we are using the running sum of the asset price, the A just now. So this is the PDE that we are going to use. Okay, the first step. Okay, before I go. Okay, our work will, the transformation will just on 1. If I were to go to the four types, we will go back to 9. Not today. Okay? Alright. Okay, let's see. We propose the following transformation. This is not Malin yet. This is not Malin transformation yet. This is just a change of variables in order to use the Malin transformation. I will give the definition of the Malin transformation later. Definitely, I'm not going to ask you about the definition of Malin, because if I were to ask that question, you will have to come in front and write the definition, right? So the one that I'm going to ask you is just something that is a general question. Okay? Okay. So V, we will transform it or change the variables into U with the same T, S, and A, time, stock, and average. But we times it with exponent negative R of tau, whereby the tau is actually the T, the big T, minus the small t, the maturity date, and any time between that interval, 0 to the big T. So the small t is anywhere inside the interval. So equation 1, so just a reminder, this is equation 1. Alright? Once we use this change of variables, so we will reach at the second, or equation 2, whereby just now we have a boundary condition, and after this transformation of change of variables, we get the initial condition with U. Okay, with the variables U, and as you can see, the terms minus RV here has been eliminated. Sorry, where am I? Okay, here. Has been eliminated. And you can see that all we have here is just all the worms, del squared U over del S squared, plus R of S, del U del S, plus something del U del A, minus del U del tau. S, A, and tau. Right? Okay, now, to reduce it to a more better equation, so that you can use it later, so you can solve it later. Remember, once we make all these changes, later on we have to go back, and you can see how it goes. It's going to be like, you have my notes, right? So you can see that it's going to, what should I say? You transform it, then you inverse it later. So this transformation like 1, okay, 1 transformation, 2, and then you will use the Malin transform, right? Twice, let's say. Then you have to inverse back the Malin, and then inverse back your transformation later. So it is quite, should I say, susah, right? Okay. I hope the others can understand the Malay, some of my Malay terms. No problem with that. Then maybe you can ask Prof. Zanaria or Prof. Sarahida. Okay. So let's do another change of variables from the U. Okay. Now we are going to use the A outside times the another function F factor of S, whereby A is actually ns, where n is a real number over the time. Okay, so we need equation 3, 4, 5, and 6 in order to change the U into the F. Okay, I think this is not a big problem to all of you because everybody here is a mathematician. Am I right? Right? Any economists? No. Alright. Alright. Okay, so this is what you're going to get. Does it look something familiar? Not yet. Does it look familiar? Okay, equation 7 is when you substituted the 3, so I'm just now I was looking at the previous presenter who's showing hands, and Professor Haidar was like, if you show hands here, there's nothing good, right? So now I'm doing the same thing. I'm going to put my hand behind. Okay, so 3, 4, 5, and 6. I'm taking all this and putting it in our previous equation just now, here, and this is what I'm going to get. Okay, like Professor Haidar said, she needs somebody who loves the analytical work, who loves the derivation, right? I like the derivation. Okay, so maybe she can hire me to be as an RA or something to do the analytical work. Okay, so we simplified this equation 7, and we get equation 8. All right, but we have said later that A is actually equals to n of n times s. So equation 8 is now equation 9. Okay, so can we take out the A here? Yes. Okay, if we take out the s here, we will have 1 over 2 sigma squared s squared del squared f plus sigma squared s plus r s del f. The A will come out. Okay, can the A be a negative? Oh, sorry. Can the A be 0? You will have A times another PDE equals to 0. Can A be 0? No. Because this is a stock price. If you get 0, then nah, you're going to lose something. There's no untung, right? If you are a shareholder, you invest some money. Do you want the return to be the same, or you want the return to go up? Definitely you want something up, right? Not up there. I mean more money. Okay, if you're going up there, I'm not gonna help you. Okay, you want more money, am I right? All right. So everybody is going that way with our economy. All right. So this is what you're gonna get. So if positive, yeah, it should be positive. That's what our intention is. It can be negative if our economy is going down, alright? So this is going to be 0, so the A is not 0, so this something times something equals to 0. Definitely the A is not 0, then the other one, the PDE is then equals to 0. And this is again our initial condition. So we don't want that R plus IN going through with us all the time, all the way through. So we're going to put that as M, okay? And again, we let the f of tau of s equals to exponent m of tau g of tau of s. Okay, there's a lot of trying and error in order to get to this analytical solution. So by using this ft of f tau of s, substituting with exponent of n tau g of tau of s, then we reduce this equation 10 into a simpler one. Now we can see that equation 11 is getting simpler. Am I right? It looks simpler, better, right? Okay. So what do we do now? Now is the time whereby we are going to use Mellin transform. Okay? The sound of Mellin is so smooth, right? So nice, but the function is not that very nice. Okay? The definition is not that. It's not that simple. Okay, this is a definition of Mellin transform for a function gs, for example. We'll put as yz, but the definition is actually the integration of g of s to the power of z minus 1 ds. I think you have heard of Laplace transform. You have heard of Fourier transform. Yes, okay. We have done with those three. But the one that I'm going to present today is Mellin and Fourier. If you're interested in the Laplace, you can ask the Uncle Google, okay, Uncle Google, the Asian option with Laplace. You will find some papers of me and my group, okay, the Laplace transform. Alright. Okay, the inverse, yz x to the power of minus z dz from beta minus I infinity to beta plus I infinity. It's just like, more or less like a Fourier transform, alright. So these are some of the properties of Mellin transform that we use in this study. Okay, you can see this is the first partial, first order partial. This is second order. So this is the transformation that we are going to get after we use this Mellin transform, and also these other two. Okay. So after applying the Mellin transform to equation 7, we will get this one, whereby we know that y is a function with respect to tau and z. But here we can see that z is not on any differential operation. So simplifying and without loss of generality, we have this ODE. And I think everybody knows how to solve this, again by using separation of variables. Okay. That's not the question that I'm going to give the prize, okay? Don't worry. Because later I will see who's going to put up your hand first. Then only I will give the prize. Okay, so at the end of the day, the solution for equation 13 will be this one. Okay, y of tau z equals to c. C is constant. Exponent of this value, half of sigma squared z squared minus z minus rz tau. Okay, you have to simplify this value inside here, then only you will get this particular term. Okay, so we have 14 as the solution for equation 13. Do you think that we have reached to our analytical solution? Not yet, because the c is not yet given. So remember, the c is a constant. Since we have used the Mellin transformation, so we also have to transform our initial condition. So in order to, we have just now g of 0s equals to phi of an s. So we are going to use the Mellin transform in order to get to the initial condition, in order to find c. Okay, so we get c here, and this is our analytical solution, which is in the transform form. Okay? Yeah, we have to inverse it back, and remember that we have made a lot of inverse, and sorry, the change of variables. So, what we do now is we invert first, okay, step by step. Just like when you are like 1 year old, you have to move slowly, right? Because you have a lot of worms here that you don't want to miss. Okay, because if you miss one of the worms here, well, I think you understand what I mean by the worms, okay? Or I mean all the variables. If you miss, then later on when you want to check the answer, you might not get back to what you want, right? So, inverse back your y, you get your g tau of s. Okay, use the inverse Mellin transform. This is what you're going to get. Okay, so but you know, just now when you did your change of variables, you have f of tau of s equals to exponent m tau g of tau of s. So you're going to times the exponent m tau back to the equation 15 in order to get your f. So remember, where does this f come from? Your f just now is from the u tau s of a, which is equals to a times your f. Remember? So your a is actually your n times s. So this is not yet your final answer. You have to go back. From 16, you use that relation and you get your u tau s. Is this your answer? No. Our equation 1 is in v. Remember? Del v del s. So it's quite a long way through. So that's why I'm asking Wei Xin to do the numerical work, so that you don't have to go. This is analytical. I mean, people who likes derivation, analytical, pure mathematician, they will love this. Okay? Okay. So last but not least, you get your v, because your V is actually exponent of negative R tau U of tau SA. But remember, your tau is T, the big T minus the small t. So this is what we get for our analytical solution. Okay, how do we prove that this analytical solution is what we want? How do you check your ODE if you get dy dt equals to something, and then you get your y in terms of t? How do you check that your y is actually the answer to your question, to your problem? Actually, I've already answered it, right? To prove that our solution is an explicit solution for equation 1, the Blackscholes differentiate 18 with respect to all del V del T, del V del S, del squared V over del S squared, del V over del A, and then plug in into the equation 1 and see if it is 0. If it is 0, that means you have reached what you want. Okay, so we have checked, and alhamdulillah, inshallah, it works. Alhamdulillah. Okay, so far, everybody still follow? Okay. Jot down, don't worry. Okay, now we'll have, maybe this one I can go like a little bit faster because everybody is almost chapter 3. Okay. I hope your stomach is still okay. No butterfly flying inside there. Alright? Okay. Arithmetic Asian option via Fourier transformation. I think Fourier is more familiar to you all, right? I think when we did our first degree, a lot of Fourier transformations, right? Okay. Actually, these Fourier transformation techniques are widely used in mathematical finance. That's why the economists, the finance people, they will need the mathematician to help them. I think that even the doctors need mathematicians to calculate the dose and everything, right? So we can be placed anywhere, right? That's what I told my students. They are so worried about their career. So I told them, you don't worry, because mathematician is needed everywhere. Not only in Malaysia, but in the whole wide world, right? Okay, so Fourier transform will actually Fourier transform has proven, can be give a closed form solution for the case of European option. Remember, European option has only 2 variables. The T, the time, and the S, that is the stock market. But here, our group used this Fourier transform to solve the arithmetic Asian option, PDE, which involve 3 variables. So that is where, actually, it is a challenge to get a closed form for this arithmetic Asian option, because geometric, you don't have a problem actually. It's not that I will say it's not a big problem, but it is not a big challenge to get a closed form. Okay, but for arithmetic, yes, it is. All right. Okay, everybody has seen this before? Yes. Am I right? So maybe this one is also in your final exam question for your first degree, right? So you have the inverse. Okay, this is your inverse. And we are going to need this in order to get back to our original function. Okay. So these are the sum of properties of Fourier transform that we use for solving the Asian option PDE. Okay. Okay, again, we are going to use the first equation that I've introduced earlier in the previous slides. So again, we will have to make some changes or some change of some variables. So in Malin just now, I used exponent negative RT U of TSA, right? So a little bit of change. So everybody need a change. So I use exponent RT. Okay, so anybody will ask me, how do you come to get the exponent RT? And how do you get exponent negative RT? Okay, that is more or less like trial and error, because you try with this one, you go through, you say, oh no, this is not going to be good. It's not going to be okay. So we go back, start with another. Just like we do numerical, right? If you try with some constant, remember if you, actually my PhD is in the Runge Kota. So when you want to do the analytical part of Runge Kota, isn't it that you have like say 4 equations, but you have to find, let's say, 5 coefficient, then 1 coefficient has to be assumed free, right? So this is more or less like that. When you deal with mathematician, it is always like that, right? So you are a mathematician, so I think you know what is actually who we are, all right? So we have equation 20. After we substitute this exponent RT of f, okay? And again, we have to assume, remember that we are going for the Fourier transform. So I have to deal with a few changes. Okay, let's say z equals to ln s, and by chain rule, you need this. And with this one, you have this another equation, reduced from equation 20 just now. Alright? And we have the initial condition again, f of tau is 0, za, and z is actually ln s, okay? And phi of z, a over t. And again, I'm coloring it in order to let you see the Fourier transform that is going to do, that I'm going to show in the next slide. So in order to get the valid Fourier transform, so I'm taking z as negative iz, alright? So this particular equation now has been changed into, you can see the difference here, and also here. This is plus, this is minus, right? Because I squared is going to be minus 1, right? Alright, so this is the one that actually I should have put it together. So the red color, you get this one, okay? The blue color, this is the one that I've shown earlier, and so does with the two colors, magenta and green, okay? So after simplifying, this is what you get. So this is more like worms, the big worms, a lot of worms, compared to the Malin just now. Malin, I think, is much better. Am I right? Because Fourier transform is something more like you get all those omega and tau and a and you know, yeah, it's more complicated. I should say that. But please, nobody fainted. I think it's still okay. All right. Further, assuming that the g is exponent of this one, actually we're trying to eliminate some of the hanky-panky terms. So again, we need to assume something. We introduce h, okay? Remember, it's still the same, tau, omega, and a, and this is what we're going to get, okay? Okay, from here, if you do the del g, del tau, del g, del a, but remember this is on omega plus 1, substitute in that equation, then you will get this, which is much, much simpler. And now applying another Fourier transform with respect to omega only, okay? Omega, this one and this one. So this is what you're going to get, okay? So don't worry about the tau or the a, because our transformation is with respect to omega. So you might ask me, why is this one still the same? Because this one is del h del tau and del h del a. So it doesn't make any difference except for this omega plus 1. So this is what I'm using. Okay, so you get the solution to the above equation, and this is what you're gonna, this is just like the previous, where you're gonna find your C. Okay, you just substitute with the initial condition, and you get your C, and the final solution is h hat equals to phi of hat. This is all in the transform form. This is all in the Fourier transform form. So what we do now is we have to inverse it back and go back all the way through. Okay, so I'm putting, I know it's not in the notes that I gave to Prof. Zanaria, because that is the first draft, actually, I told her. Okay, so here in this slide, I put the transformation that I used. So you're not going to see like, oh, okay, where does this come from? Okay, I know it's not easy to read. Okay, all right, so this is what you get. So apply the inverse, But remember, your H is not your final solution, right? Okay, so we use the back substitution again. So we have the H, tau, omega, and A is actually times with the exponent of these particular terms where you get your G. So the G now is the whole thing, this whole thing, times with the exponent of that terms. And then using again, remember we do twice Fourier transform just now. Am I right? So now we have to inverse is also twice. So there's another inverse of Fourier transform whereby you will get your f of tau negative IZA. So this is the solution. But remember just now we put Z as minus IZ. So again you have to do a little bit of the inverse of changes of variables. So I put again Z is equal to ln S, therefore your S should be exponent of Z. And your tau is actually T minus the small t. So we have the f of tau ZA. Are we at the end of the solution? Why? Very good, very excellent students I have here. Because what? The V is actually exponent RT F of T S of A, right? So one more and then you get the final solution. I feel very guilty because I brought only two presents because everybody did very good. But anyway, who's going to be very fast? They will answer and she or he will get the present. Okay, so again, to prove that equation 22 is the correct solution, the one that we get, so we differentiate it again upon T respect to A and respect to S, substitute it again in question in PDE 1, the Blackscholes models that we have modified a little bit. And when it produces zero value, that means it satisfies the PDE. 5 minutes late. I'm supposed to stop at 12:30. I think you should. It's okay. Okay. Anyway, I've come to the end of the slide. Don't worry. In this study, we reached the problem of solving the PDE using transformation methods. Okay. If you want to use Laplace, then you have to have a look at our work before, because we have done Laplace. Maybe you can use other works such as Laplace decomposition method. So that will be different, right? Or maybe you can use, I don't know whether it works or not, VIM, rational iteration method, or HPM. Yeah, maybe, because VIM is a series actually. And HPM or HAM, I think you know what HAM? Homotopy analysis method, homotopy perturbation method, those are all series. Maybe it works, but it's going to be more complicated, because you can see with all these PDEs, it's going to definitely PDE is something that will have to deal with most of the analytical work. Maybe like Prof. Sarah, I was talking to Prof. Sarah about the PDE. Maybe you can use methods of time just now, and the Prof. Sarah was saying something like reduce order, and you will get a system of ODE. It will be better. I mean, ODE you can use Runge-Kutta or any modified Runge-Kutta. So many of you have, I think, Prozanaria, Zarina also. There's a lot of block method whatsoever, right? Okay. Okay, I was proposing something. Our approach could be extended to the continuous arithmetic option with constant dividend here. Okay, these are the references, and I thank you. Okay, ready for the question? No? Okay, first question. Whoever put up the hand first, you get the prize. But the answer must be correct. Name 2 transformation techniques that are used in this study. Okay.
The first one was one mailing transformation.
Okay,
and
right. The other one
is the Fourier transform.
Fourier transform. Congratulations.
Thank you.
Congratulations. Okay, one more question. What do you think the question will be? That's Okay, what is the name of the model used to get the analytical solution of Asian option pricing? The name of it. Blackscholes. Okay, with that I end my presentation. I hope everybody enjoy it and get something out of it. Okay, Assalamualaikum.